So starting today, we're going to talk about the charging system, and I've got in my hand here the heart and soul of a charging system, which is an alternator. And this is a DC generator. Sorry, it's an AC generator, but we convert it to DC. So a generator is any device that makes electricity. This one makes alternating current. We convert it to DC with a series of diodes. Everything in a car has to run on DC because our storage batteries are all DC. So we use an alternator to make AC and convert it to DC. So everything on the car runs on DC with some small exceptions. So the components of it, first we have a battery. That's our power source, PWR, my abbreviation. It's our power source for the alternator to get it initially charging. Secondly, I put there alternator field. So the magnetic field inside an alternator is energized by the automobile's lead acid battery. So then we have an alternator, which is an AC generator. It's going to make AC current. Again, we convert to DC with a series of diodes. We'll talk about that. We have some sort of a pulley, and we have some OAP and OAD alternator pulleys. These are basically decoupling pulleys that we're using on modern cars to prevent vibration and to reduce drag and things. And we can look at that on that YouTube video to learn what they are. But we have alternators with types of alternator pulleys. We have a voltage regulator, and the voltage regulator is used in the system to control voltage and current output, like it says there. So it is the voltage regulator's job to decide how much voltage the alternator is going to make, how much current it's going to produce at any given time. An alternator is an on-demand charging device, meaning it makes power to meet demand. It is not just charging at max output all the time. It's only charging at what is it's being asked to give, if you will. And on modern cars, the powertrain control module, the engine computer, is involved in deciding how that alternator is going to charge, how much current voltage it's going to charge at. So let's continue here. We also have a voltmeter on the dash that's going to measure system voltage. Old school cars in the 60s had ammeters on the dash. We now use voltmeters on the dash, or we'll just have a battery icon, a red battery icon, which is telling you that the battery is not being charged. It is not telling you that the battery is necessarily bad. It does indicate that the battery may drain because it's not being charged. But when that red battery icon comes on, that's because you have an alternator that's not charging the system anymore. And one other thing, sorry, the camera's just a little bit low. We've got computer controls controlling the voltage regulator. So the PCM, which is the engine computer or powertrain control module for OBD2 terminology, is controlling the voltage regulator's output. And years ago, the computer wasn't doing anything to the charging system. Now it's actually controlling the voltage regulator. So we can do things like we can actually shut the voltage regulator down and freewheel the alternator so that we can put more power to accelerating the engine when we're trying to get power on a modern vehicle with a smaller engine that saves weight to reduce gas, fuel consumption, etc. So how is an alternator constructed? Well, first it's got a rotor. And a rotor is a rotating electromagnet. So here's a rotor that I'm spinning right here. There's the rotor. It's a rotating electromagnet. It says that that electromagnet is called the field, and you can look inside in the center between these pole shoes. You can see a spool of solid copper wire, approximately 16 gauge, plastic coated, that's wrapped around there, and that's what makes essentially the field or the magnetic field. So like it says, you got a spool of plastic insulated 16 gauge wire. There are north and south poles, so these are north and south poles to intensify the magnetic field and kind of set the magnetic field up. And it spins in a housing with a bearing back here. You can't see the bearing on this one. And on the other end, it's supported at the front by a larger bearing. And the reason for the larger bearing is that that's where all the tension from the belt is pulling on. So that larger bearing is right behind this pulley in here. Okay, at the front of the alternator. Next, we have what's called a stator. And the stator is a group of 3 or 4 pairs of wires, as you can see joined here. 3 or 4 pairs of wires, and this one's actually got 3 pairs, and all these wires are joined at the other end, and I'm not sure on this stator if I can see where they're joined at the other end. I'm looking, and I don't see it, but you can see 1 pair, 2nd pair, a 3rd pair. Sorry, up where you can see 3 pairs, and they're joined at the other end. So it's 3 separate windings of 16 gauge wire joined. Opposite ends connect to the diodes, and this creates 3-phase AC diode rectified output. So when we say 3-phase, there's actually 3 different loops of wire that are producing an AC current, alternating current. And we use diodes to rectify or change the AC into DC and give us diode rectified output is DC. Okay, so we're going to turn this, there's our 0 set line, this positive and negative voltage flowing in one loop, another one, and finally another one. We're going to turn it into all DC, so it's all positive AC voltage swings. Okay, so we also have brushes inside the alternator that are going to contact what we call the slip rings of the rotor. So here you can see the slip rings right here, these 2 round copper contacts, and there's the brushes there. These let me set this down. These spring-loaded, they're sintered bronze, which is like a powdered metal kind of construction that rides on right on this guy. So this would go inside there and ride on that slip ring with those brushes and bring a battery positive, battery negative, but actually it's a voltage from the battery that's controlled by the voltage regulator. So the voltage regulator decides how much current this rotor gets, so how strong a magnetic field it's going to make, and consequently how much output it's going to make. There are bearings, and you can see this sealed roller bearing that's inside this housing half to support one end of that rotor, and then the other one's at the other end. And then a modern alternator has some fan blades attached to the rotor on the inside of the case to blow air through all these slots in the case here for cooling. Also, it reduces weight to have it with so many openings like that. Okay, so we've got a rotor, a stator, we've got a housing, I think it's going to come up in the next slide, brushes, bearings, and a fan. Okay, so I didn't put the housing down there and should get that to focus. There it goes. So how does an alternator function? How does the thing actually make power? Well, we're going to make power by what's called electromagnetic induction. And I like to be able to take complicated words and break them down so we can understand them. So I'll grab my pointer here. So a magnet, all right, can be made with an electron flow. So we can flow current through a coil of wire and make an electromagnet, as opposed to a permanent magnet. You know those little cool permanent magnets your mom gave you to get you out of the kitchen for a couple hours when you're a little kid. You pushed them around the backyard, or you turned them around and they attracted to each other. So we're going to make an electromagnet. We're going to cause induction. Induction means to put into. So we use an electromagnet to put a current flow into an adjacent conductor. So current flowing in the rotor from the battery, regulated by the voltage regulator, is going to create a magnetic field. The stronger the magnetic field, the more output the alternator makes. That spinning magnetic field is going to pass a stationary conductor, or several stationary conductors, which is what the stator is, causing current flow in the conductor. Okay, so basically if I spin this rotor, and I've got stationary conductors around the outside called the stator, and again this guy fits right inside there and it spins, I'm going to get current induced or put into these windings. And depending on the amount of windings and the size of the wire, I'm going to get a current boost. I'm going to make, get a voltage boost and a current boost. So what you have in this picture, and I really like this picture even though it's a little bit, the focus isn't fantastic. Unfortunately, this guy doesn't focus so well on it. I don't know if it'll do any better if I come closer. I'll go further. Yeah, it's really nice. If I get out of the way, it does a little bit better. Okay, so let's talk about this. So let's find something that we can understand. Well, there's the battery. That's our universal DC battery ground symbol. So this is our positive side, negative side. So on the positive side, and this dashed line all the way around here is the alternator itself. So we got a battery, and outside this, in the instrument cluster, we have a warning lamp, which would be our picture of the little battery. We've got an ignition switch that's kind of controlling where power goes, etc. So everything inside this dashed line is the alternator. So let's try and figure out things. So first, let's look down here. Here's the rotor with its coil of wire. That's what's in the middle of this guy right here. So this is the rotor in the middle inside here. Right inside there, you can see those coils of 16 gauge plastic coated wire. Sorry, the glare is a little tough. And then here's the slip rings on the rotor. Those are the brushes. And of course, this isn't to proportion because the brushes aren't nearly as large as the actual coil of wire. Then here's the 3 stator windings joined at one end. And the other end of each stator winding is going to a pair of diodes. So you have 2 pairs here, here, here. And then you've got some more here. The whole job, as this rotor spins and induces current into these 3 windings, it goes to these diodes, and the diodes basically, like a little maze, cause everything to flow in one direction, okay, back to the battery. So we're taking the AC and we're turning it into DC. That's a little capacitor, a little a little electrical capacitor. And then all of this is our voltage regulator, which is a little more complicated circuitry, but this voltage regulator is going to control how much current goes back to the battery. So current's coming out of here, going up here, and going back into the battery. So the way this is controlling this current output is by controlling what goes into the rotor. Okay, so all this stuff here is the voltage regulator controlling voltage and current to the rotor. The output of the stator goes into the diodes, turns it into DC, and charges the battery. So these are the universal symbol for diodes. That's a transistor, 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 a resistor, 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 coil, 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 ground symbol, capacitor, ground symbol, diode, 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 diode. Okay, so you get an idea of what those things are. Let's continue on here. So how does the alternator function? So what we call diode rectification. So the diodes are going to rectify or channel the current flow from AC to DC. We use 3-phase AC output and we convert it to DC. Let me show you a pair of diodes. So here is a pair of diodes, or sorry, a diode group of diodes. There's 1, 2, 3, 4 diodes there. 1, 2, 3, 4. So there's 4 positive and 4 negative diodes. The brushes, you can't see them, they're not in there right now, but they would be down in here. This is the voltage regulator right here. This is a heat sink, so this guy right here is the voltage regulator on the back side. This guy's controlling what goes to the brushes. These guys here, these 4 negative, 4 positive diodes, are controlling the output here that goes to the battery. So you have some more. There's another group of 8 diodes. 6 diodes. 3 positive, 3 negative diodes there, and their output going to the battery. Here's a Subaru that wasn't charging right. If you can look really carefully, see if you can see here. I get the camera way up there. It's a little hard to tell, but these are burned. These diodes, some of them are burned right here. So this was a 95 Subaru Legacy. Had burned out diodes. It wasn't charging properly. You can actually replace these, but typically we just replace the whole alternator with a rebuilt unit. So here's our 3-phase diode rectified output. And all this is showing is, in this scenario here, where current is flowing this way through these 2 coils, you can see how current is trying to go this way and how the dashed diodes are blocking the current. Sorry, the dashed diodes are not in the circuit. This one's blocking the current. This one's letting current go through to the battery. When we switch direction, then current can go through like this, go through that diode like this, go up like this, and go back to the battery. Here's scenario B, where the current's going this way or the current's going this way, and we use these diodes to get it to go to the positive battery terminal. And then finally this way and this way. So these are our three phases, and where the current's flowing in one direction and in the other direction. Okay, so as the North Pole approaches a diode wind or a stator winding, current flows in one direction. As it goes away, it flows in the opposite direction. So that gives you a little idea of how we convert the three phases of alternating current into DC to charge the battery. Let's go further. So now that we've looked at the components, let me see if I can get this thing to focus here. Sorry, why it does that sometimes, I don't know. No, it's not going to do it. So let me try and get it focused. All right, there I got it focused. So, oh, and it goes out of focus. I'll try one more time. So it seems like as long as I stay out of the picture, it seems to focus. Of course, now it's not focusing. So I'm going to try this one more time. There it focuses, and if I bring it back, hopefully, no, there it goes. Okay, so let's try it. So how do we diagnose charging system? First, we're going to check our battery cables and condition to make sure we're full of electrolyte, our cables are clean and tight. We'll look at the date code in the battery, make sure it's not close to 7 years old, and it has a resting voltage of around 12.6 volts. So we also want to measure at the positive negative terminal while the engine's running, make sure we have 13.5 to 14.5 volts running voltage. Okay, that usually tells us that if we have 13.5 to 14.5 volts, we know that the alternator appears to be charging, although that's not a definitive test. Then we want to make sure that we have the correct number of amps being provided by or being produced by the alternator at 2000 RPM while maintaining a minimum of 12.6 volts. So when we do an alternator output test, we're going to suck power or load the alternator and see if we can get the correct number of amps at 2000 RPM while maintaining 12.6 volts. Most modern cars will not allow you to do an alternator output test anymore, but they have a specification. They say start the car, run it at this RPM, turn on the high beam headlights, turn on the AC system, and then measure the current draw out of the current flow out of the alternator or at the battery. And we can do that with that 600 amp inductive clamp that we used in conjunction with our voltmeter yesterday when we were doing starting system testing. We also want to make sure there's no battery spills, no battery acid spills, which would indicate an alternator that was overcharging because the voltage regulator was malfunctioning. We also want to note if the headlights are normal brightness. So overly bright headlights are indicator of a voltage regulator that's overcharging the battery. Further, we're going to do an alternator output test. And this is the test that tells us, can the alternator give us our rated amperage output at 2000 RPM and maintain a voltage of 12.6 volts. And there is a thing called a full field alternator output test that's not really done anymore, but this gave us a way of bypassing the voltage regulator and forcing the alternator to produce a maximum output. And I do have a car here that we can still do that on, and we don't do it on modern cars with computers involved, but it was a way of us deciding, is the alternator working correctly or is the voltage regulator malfunctioning? So that's called a full field alternator output test or regulator bypass test. And then we can test the rotor and the stator for opens and grounds, and we'll do that. We'll take an ohm meter and just check the rotor. We'll check the coil in the rotor to make sure it's not open, that it has a couple of ohms of resistance, something like 1 or 2 ohms, and it's not grounded to the shaft of the alternator. Okay. So just a little bit about repair and replacement. Most of the time, and again, sorry for the lack of focus, but most of the time on modern cars, we are, come on dude, focus. Most of the time we are replacing with like a rebuilt alternator. But the brushes are wearable, replaceable parts. The bearings are repairable, replaceable and repairable parts. A diode assembly can be replaced, although we're not doing it on a modern car, a couple $100 alternator max. But on something very large, like a piece of farm equipment or a big truck, we may replace the diodes, brushes, and bearings and the voltage regulator to rebuild that alternator because it might be too expensive or difficult to get a new assembly, but it depends. But the brushes, the bearings, the diodes, and the voltage regulator can be replaced, although not really commonly done anymore. But when they're rebuilt at the factory, they're going to sand the slip rings where the brushes contact. They're going to replace the brushes. They're going to put new bearings in it. They'll probably check the stator and the rotor for opens or shorts to ground. The voltage regulator, whether they replace it or just check it out, I honestly don't know, is what a production rebuilder does. But those are all replaceable parts. Okay. And I mentioned just sanding the slip rings so that you get a good contact where the brushes are hitting those slip ring contacts. So what we're going to do now is we're going to do some testing. So I'll pause the video here or stop the video here, and then I'll make a second video that shows us doing some testing of the rotor, of the battery, of the charging system, etc. So we'll go to that now. Thanks for your attention, by the way.